Hello everyone. So in this tutorial we will see the lead code problem longest increasing path in a matrix. So in this problem you are required to solve this function longest increasing path that takes a matrix as its parameter. Okay. The return type is integer. So you have to return the length of the longest increasing path in matrix. The matrix consists of m rows and n columns. Okay. So let's see what are the rulings as to how we can traverse or we can form paths inside the matrix. So to start off, I can choose any of the random cells of the matrix, any of the random cell given here. I can choose and I can try visiting any other cell from it. But what's the ruling for that? So let's suppose I choose this 6 as my starting point, right? So from here, these 4 directional movements are allowed: 6, 8, 9, and 1. Okay. Let's say these 4 cells are the neighbor of my current cell. To whatever cell, okay, to whatever cells this current 6 is sharing an edge. Okay, let us call them neighbors of my current cell, right? So the current cell is 6, it has neighbors 6, 8, 9, and 1, these 4 cells. So from my current 6, which of the neighbors I can visit? That's the question. So among all neighbors, whatever neighbor that has a greater value than my current cell, I can visit them. So if my current cell is 6, I can visit neighbors 9 and 8. Okay. So we see that whatever is my current cell, I can visit a cell that has a value greater than that, right? So the path becomes increasing in nature. I can only visit from my current cell of any other cell that has a value greater than my current cell. So that's how we see the paths are becoming increasing in nature, right? Now it's not worthwhile that we should start off from any random cell. Okay, there are particular cells inside the matrix from which you can definitely, or those cells can be definitely chosen as the starting points of our paths. Okay, what are they? Let's try to find out. Now, observe one thing. If I say I start off from this 6, I will start from this 6. I can visit either 9 or 8, these two cells, right? So, the these two choices are giving rise to two paths, 6 to 9 and 6 to 8. So, both of them are having length 2. Okay, any bigger length, okay, any bigger length of path I can find out such that inside that path this middlemost 6 is also lying. Okay, can we form that? If we observe, we have this one. Okay, if I choose this one as the starting point and visit 6 from here. Okay, one has a value greater than 6 as well as 1 is a neighbor of 6, right? One is a neighbor of 6. Definitely I can visit this one first, and then I can try visiting the middlemost 6. What we can observe that if we include this one, whatever possibilities we had from this 6, okay, from if we start at this 6, the maximum path or the maximum length of the path that we can form is 2. But if I include this one, the same result gets increased to 3. Okay, 169 or 168, a longer path we are getting of length 3, inside which 6 can reside. Okay, so our answer is getting better. Okay, now observe one thing. If I am at this one, what are its neighbors? 6, 2, and this one. Okay, so from this one I can visit my upper 6 and lefter 2, right? But this reverse is not true. This 6 is greater, so from 6 I cannot come to this one, and from this 2 I cannot come to this one, because again 2's value is greater. Since the writer one, okay, this is my current cell, the writer one that I have has a value equal to that of my current one. So again from here as well I cannot come to this one. Okay, so one is such a cell, this particular one is such a cell, okay, which cannot be visited from any of its neighbors. It's not possible. But any of the neighbor that I have might be possible to be visited by this one, right? So I say this particular one can be one of my possible starting points of any of the paths, okay, that it can be a part of. Okay, there are certain others, let's look at them. So similarly, we can see this one, okay, cannot be visited by this one or this one, okay. But if I start from here, I can visit this 8, right? One possibility is there. So one, the cell value 1 that resides at row number 3, column number 2, as well as the 1 that resides at row number 3 and column number 3. These can be my starting points, okay, of paths. As well as this 4, observe here, from 9 as well as 8. I cannot visit 4. But the reverse is true. From this 4, I can visit 9. And from this 4, I can visit 8 as well. So what I say, 4 also is serving as one of my possible starting points, right? Let's try to accumulate what are the paths possible inside the given matrix that we have. So yeah, I have marked the 3 starting possible points that we have. So let me try visiting all the nodes starting from this one. If I start from this one, I can visit 6 as well as 2, okay. So I go to 6 as well as I go to this 2, right? Now, yeah, from this 2, if I try forming or I try visiting more nodes or more cells of my current matrix from this particular 2, what are the possibilities? So from this 2, I can visit this 6, right? 6 is a neighbor of 2 as well as 2's value is lesser than 6. So I can, from this 2, I can visit 6, definitely. So from 2, I have visited 6, okay. From this 6 that resides at row number 2 and column number 1, I can visit 9. That's a possibility, right? This particular 9 from here I can visit. Okay, I've marked it. Yeah. Now, from the middlemost 6, what were the possibilities? I can visit 8 as well as I can visit this 9, right? These were the possibilities for us. Now you can see all the explored paths, okay, using this 1. The starting point 1, we have visited that, right? Now we can see if we start this particular one as our starting point, from this one, I can visit only this 8. Okay, only the above or its upper 8 is possible to be visited. Now, one of the only left cell for us is this 4, and from this 4, I can visit both 8 and 9. Okay, so what you are observing from the structure we got, okay, as well as one observation I would like to show you is that if suppose from 1 to 2, okay, there is a path from 1 to 2, the reverse is not true. There is no path from 2 to 1, right? Because I can't visit 2, I can't visit this one from this 2. That's not possible. 2 has a value greater than 1 as per the rulings of the question. So what we say, the structure we are able to form, okay, we have accumulated all paths inside a structure. This is called a DAG, directed acyclic graph. Okay, it cannot have a cycle. Why? Let's have a visualization. 1 2 6 9. This is our one of the paths, right? Starting from this one. Okay, to have a cycle from any of, let's say, this node, okay, it should have, I can visit this node starting from this one, okay, but the reverse is not true. Any of its ancestors, the ancestors of 9 are 6 and 2. I cannot visit them back. I cannot visit them back. Why? Value of 9 is greater than 2. So there cannot be an edge between 9 and 2. Okay. If I can go from 1 to 2, I say 1 has a directed edge between, or a directed edge to 2. Okay. The reverse is not true. From 2, there is no edge to 1. That's not possible. Why? Because value of 2 is greater than that of 1. Okay. So I say why 9 should not have a back edge towards 2, because value of 9 is greater than that of 2. So I say, as per the given question, the entire structure that we are able to form is a DAG. Now I have drawn the entire structure or the DAG here. Now what we can say, okay, if we start from this one, okay, our this entire path 1 2 6 9, right? Starting from this one, if I try visiting this 9, this is giving me the maximum length, okay, 1 2 6 9. This is having the, among all other lengths, okay, inside the DAG, this is having the maximum length, or it has 4 nodes inside itself. So I say the maximum length that any of the path can have inside my given DAG is 4. Now how to find out that 1269 has the maximum length. How to start off with that? Okay, let me mark. Okay, let me mark my starting points 1, 1, and 4. Okay, they are the starting points of my node. So I can say my path starts from this one and it has a path length of 1 initially before I have formed any of my paths. This particular one has a path length of 1 initially, and this one as well and this 4 as well has path lengths of 1 and 1 each. Okay, why? Right now for this one, the second one and this 4, okay, we haven't added or traversed any of its neighboring nodes. So we cannot say what nodes are there and what is the maximum path of those nodes we can visit. So we say that, okay, initially they are the starting points. So inside the chain, there are only one node. Okay. So that will constitute or give rise to the path of length 1 only. Now let's try visiting the neighbors. Now from this one, I can visit this 2 and 6, right? What can be the maximum length if I come to this 2 and this 6 from this one, what can be the maximum length that I can have? So initially 1 has a path length of 1. So right now 2 can be visited at a maximum length of 1 plus 1. Just 1 more than my previous node. Similarly 6 can be visited at a maximum length of 1 plus 1. Not more than that. Right? Okay, fine. If I again try to dereference this one, okay, if this is my starting point, with what maximum length I can visit this 8? What are the possibilities? So since the path length in which this one is residing is 1, so from this one, if I try visiting this 8, the chain will be having maximum of 2 nodes. So as of now, from this one, if I try visiting this 8, I can visit this 8 at a maximum length of 2. Okay. And similarly for this 4, I can visit either of 8 or 9 at a maximum length of not more than that. Okay. Let us refresh this. So what we have observed is this 6 can be visited as of now at a maximum length of 2. This particular 2 can be visited now at a maximum length of 2, as well as this 8 and 9 can now, as of now, can be part of a length that has a maximum length 2. Okay, these are the current status. Now see, from this one, this 4 and this first one, okay, we cannot visit any other nodes. Whatever nodes we could have visited, we have visited that. So let's peel off. Let's eradicate them from our current graph. Okay, let's remove them. Now, why I say that this one, this 4 and another one were my starting points. Why? Because from any other node I cannot visit them. Right? That was not possible. So it was feasible for us to take this, okay, or the nodes inside our graph that does not have any in degree, right? We were taking them as our starting points. Okay. Now what next nodes to traverse inside our graph? Okay. So we say that what set of nodes inside our graph right now we have that don't have any in degree. That is this 6 and that is this 2, right? So from this 6, okay, let's try them. From this 6, if I try visiting 8 and 9, what can be the maximum length? 2 can be visited, okay? 2 can be a part of, as of now, maximum length 2. So now if I try updating this 8 and 9, what maximum value I can get? I say that, okay, this 8 and 9, if I try to visit from this 6, earlier we have visited them from either 1 or either 4. But from this 6, if I try visiting this 8 and 9, I can have maximum value of this 2 plus 1, as well as again 6 can be visited at a maximum length of 2, and so this 9 can be visited at a maximum length of 2 plus 1. So I have updated that. I have to always keep a measure that, okay, particular node can be visited at what maximum length. So earlier it was 2, now I am getting a better result, that is 3, so I have updated that with 3, right? Okay, so now if you see, we are left with one other node, that is 2, and this 2 does not have any in degree right now inside our graph, right? So yeah, from this 2, if I try visiting this 6, okay, that can again be visited at a maximum length of 2 plus 1, right? Okay, so see, from 2 and 6, whatever nodes could have been visited, we have visited them. Okay, now they are of no use for us. Okay, so let's remove those edges, whatever this 2 and 6 were having to other nodes. Okay, so we have visited 8, 9, okay, and 6 at a maximum length of 3. That's what we have seen. Now 8 and 9, okay, they are the current nodes for us which have not been visited, and they are having no integers right now inside them. But again, from 8 and 9 we cannot visit any other nodes, right, of the graph. So from here the path stops. The 8 and 9, these are those nodes where the path stops. Okay, but one node we have, that is this 6, which does not have any integer, okay, and have not been visited yet. So let's try forming a bigger length path using this 6. So I say that, okay, there is only one node from this 6 that I can visit, that is this 9, and can have a max. This 9 can be visited at a maximum length of 3 plus 1, right? So this 9 is visited at a maximum length of 4, right? So if we try to accumulate the results, the first one that we have can be visited or can form a chain of maximum length 4, sorry, maximum length 1. Then this 6 and 2, what we have visited from this one, can be part of a chain inside our graph at a maximum length 2. Then 8, 9, and 6 can be part of the chain, right, at a maximum length 3. And this 4 can be part of maximum length of the chain 4, right? Again, the other 1 and 4 that we have, other starting points, they too will be, can form a chain of maximum length 1, right? So this is the data that we have got. What we can say, whatever node stores the maximum value, okay, that what is the maximum length of chain this 4 can form, that's 4, right? It is having the maximum value. That will give us the result that what can be the length of max, or what can be the maximum increasing path length inside the matrix I can have. How we have find that? Okay, whatever node I have, okay, whatever node inside my current matrix stored the maximum value, this 4, right? And now what you have seen, that we have first found out what nodes don't have any integer, right? Okay, then we removed all the edges to whatever cells or to whatever nodes a particular node without an integer can be visited to, right? Once we explore them, we remove these edges. Okay, so what we are doing, we are applying topological sort here, right? We are applying topological sort here, and using this we should be able to find out what is the length of maximum chain inside the matrix that's increasing in nature as well as that has the maximum. Okay, how will that be possible? Inside the matrix, we'll just, for any particular cell, we'll just store the value that, okay, this particular node or this particular cell's value can be a part of the maximum chain length. Okay, what that chain length value is. So in our case, this particular 4 we have found out to be, sorry, this particular 9, right? Okay, no, it was, yeah, sorry, this was not 4, this was 9. Okay, I've written it wrong. This particular 9 can be a part of maximum chain length to be 4, right? Sorry for the disturbance. So the value inside the cell of 9 should be stored 4, right? And this 4 will be serving our answer. So let's try move ahead with the code. How should we do it? So first, let's form the edge structure of the graph. For that, let me keep a map of pairs. And that will point to what? Again, some other cell, right? And that is again determined by a set of pair. Pair here determines what is the row number and column number. Okay, keep that in mind. So yeah, I've kept the edge, and let's try forming the edge structure. So let me traverse all the matrix cell one by one. So I say So for a better understanding, let's try to find out the number of rows inside my matrix. Let me keep it inside n, and okay, let's keep it as the analogy of the question that m determines the number of rows and n determines the number of columns. So I've kept it. Now let's try traversing the cells. Sorry, this will be m, and here inside the j we will be going for n. And yeah, so let me try forming the edge structure. What I will say, if suppose the writer cell, okay, how can I visit that? I say j plus 1, the value of it is less than n. If that's true, as well as one other thing is the matrix, okay, the matrix value of my writer cell, whatever I have, that should be greater than, right, the current value that I am having inside my current cell, that is at ith row and jth column. If this is true, then inside edges of I and j, inside edges of I and j, I can just push back the value that's again a pair I and j plus 1. Similarly, we can go for others. Okay. So if I'm looking for the lefter cell that I'm currently right now, so again there is one condition, its value, the column's value, that is j minus 1, should be greater than or equal to 0. Again, what should happen? Matrix of I and j minus 1, right, should be greater than the value of my current cell. If that's true, we can go ahead with the same thing inside edges of ij. I can just push back I and j plus 1. Similarly, we can go ahead by traversing the upper and lower cell that we have from our current cell. Okay, here we will just compare whether the conditions I plus 1 is less than m or not, or I minus 1 is greater than equal to 0 or not, and if the values of my upper cell or the lower cell is greater than my current cell or not. If they are so, inside the edge structure of ij, I will be having two more values, I plus 1 j and I minus 1 j. Okay, these are the conditions for forming the edge structure that we have. Another thing we need is that what is the in degree of any cell, right? What is the in degree? So let's keep that, and again I will be having a pair that for any of the cells that I have inside my matrix, what is the value of its in degree? So what we can say is that, okay, okay, so let's do one thing. Before having any value inside the in degree, let's initialize every cell's in degree to be 0, right? So let me go ahead one by one to all the cells. So what I say initially, in degree of my current cell ij, let it be 0, right? Now, while I'm forming the edge structure, let's say this ij is having an edge towards I and j plus 1. So this particular cell I and j plus 1 as a node has an in degree, right, from I and j. So we say, if this is true, if the condition is true, in degree of I and j plus 1, okay, that increases. Okay. Similarly, for other condition as well, we can say if these conditions are true, in degree of firstly I and j minus 1, this increases, and similarly for other two conditions as well. Let's write them. Okay, so we have written that for the upper cell, if the condition is true, the in degree for the upper cell, okay, since I and j is having an edge towards I plus 1 and j, the in degree increases for I plus 1 and j. Similarly for I minus 1 and j. We have written that. Okay. Now the edge structure, okay, this is over here. Let's try to grab, okay, what particular nodes, okay, or what particular cells are having no in degrees or having 0 in degrees. Let's try to find out that. So let me go ahead one by one again for every of the cell, right? Or yeah, we already had that in degree, right, for inside us in degree map. And let me initialize a queue first, okay, to arrange for our topological sort. And this will again be having a pair. This will be of type pair only, because we are determining a cell as the nodes of the graph. So I say, while I'm traveling or while I'm traversing, okay, all the all the keys that are present inside my in degree, whatever key, okay, whatever key is having an in degree value to be 0. So I write if it of second, okay, is having a value 0, just push that inside my queue for starting my topological sort. So yeah, since that's of type pair, we are pushing the value of it of first, that whatever we have inside it of first, that is going inside the queue. Okay, now let's try starting our topological sort. I say, while my queue is not empty, okay, what we are gonna do first, let's take that pair out, whatever node we have. So since that's of type pair, let me keep my front and let me access the front of the queue and let me pop it out. Okay, that's of no use firstly once it goes out of the queue. And again, so let's keep the answer. Okay, what's the maximum chain length a particular node that I'm visiting right now can be a part of? So yeah, what I'm gonna do is, firstly I'm gonna keep an answer, again a pair of map, a map of pair rather, sorry, and this will be having an integer, and I'm just naming it answer, or maximum length rather, let's name it max length. And let's go ahead, and yes, whatever we have found out, whatever nodes we have found out that don't have any in degrees, for them the max length of it of first, right, max length of it of first for them goes out to be 1. Okay, they can be a part of, firstly they are the starting points, so with them I can start. So their starting point of the chain with a length of 1, that's why I've initialized them to be 1. Okay, now let's move ahead. Okay, firstly what I will do, what are my current neighbors? Okay, this is my current front, my current node that's stored inside my variable f, that's the front of my queue, and I will go to its neighbors one by one. Okay, let's go ahead. So yeah, one thing we haven't done correct is this will be vector of pairs. There can be many pairs, right, that can be my neighbors, so this will be vector of pairs. So let me try visiting all the neighbors of my current node that's stored inside f. So yeah, that's those neighbors are again pairs, right? So what should we do here? Let's keep another variable neighbor. Let's name it neighbor, and that will be having the value of edges of f and I. Okay, whatever is the ith neighbor of my current node f. Okay, that will be stored inside the variable neighbor. Okay. So two things I can do here. Okay, two things I can do. Firstly, since I am visiting this neighbor, what I can do here is one edge. Okay, it is having one edge towards itself from this particular node f. Okay, that goes down. Okay, I have visited this particular neighbor from the node f. So what I say, in degree of my neighbor goes down by 1. Okay, that's one thing that I have done. What's next? Okay, so I can visit this particular node f with some maximum length, right, with some maximum length. So what I say, let's try doing one thing, let's try and update the maximum length that this particular neighbor is having. Okay, let us keep that to be, okay, Let's update that. So what I say, firstly, I don't have any, this particular neighbor might not have any maximum length with itself, right? So let's do one thing. Whenever we are updating the in degree value, let's update the maximum length of any particular node we have, right? Any particular node we have to be 1. At least all of the nodes, if they are having the same values inside the matrix, they can have at least value of 1, okay, inside the chain of itself, we can say that. So what we say, maximum length of neighbor can be updated to either its current value, right, whatever value currently it has, or with whatever value I have visited the node f, okay, this node f with whatever value I have visited. Just let me remove this, plus 1, okay, or just let's drag it down here, not more than that, right? Okay, fine. Another thing, since I have visited this, I will check one thing. If its in degree has reduced to 0, its in degree has reduced to 0, then what I will do is I will push it to the queue, okay, for traversing more paths using this particular node. What I say, inside the queue, push it. Push what? The neighbor. Yeah, we are done with this. And after our topological sort is over, right? After our topological sort is over, since we don't need to bother about the cycles, because this particular graph, whatever it gets formed, does not have any cycle, that's guaranteed. And yeah, after we are done, we can try traversing all the nodes again, okay, and can take out my answer, okay. If let's keep it to be 0 initially, and what we say, while we traverse everything, every other node inside the max length, okay. So let us try by traversing the max length. I say max length dot begin, and let's go ahead till the time we don't reach the end, as well as let's move one by one. I will just update my answer to be maximum of whatever it has currently, as well as whatever value I get, okay, from my current node's value. So this is done, and once this is done, we can return our answer. That's all. So our code is done. Let's try running this. So if I try running this, the first test case is passing, and let's try submitting this. So yeah, our entire problem has been accepted. Now let's try judging what's the time complexity for our problem. Now see, if you want to visit every node, right? Every node inside the graph we are visiting. So how many neighbors a particular graph is having? So I say this is my cell. It can be visited by at most 4 other cells, right? So of any particular node that I can form from this cell can have at most 4 visits, okay, at most 4 visits. So in the worst case, I say I am visiting any node n of my graph 4 times, and all of the nodes we are definitely visiting. So I say I can solve this problem in not more than big O of, okay, 4n. Since 4 is a constant, we can remove this and we can solve the entire problem in big O of n time, okay, where n is the number of nodes or the number of cells that we have. So if we simplify, we have m cross n, right? We took here n as nodes, okay. Let me try bringing that in terms of my given constraints. So yeah, let's not use n here. So we say big O of number of nodes. We can solve the problem. How many nodes are there? M cross n. So I say I can solve the problem in not more than big O of m cross n. Okay, big O of m cross n operations. Fine. Now, what is the space complexity using topological sort that we have used? So inside our queue, at most in worst case, all the nodes of the graph can reside, right? All the nodes can reside. So we say that we require extra. How many nodes are there? M cross n. So extra m cross n spaces we require. So we say our space complexity is big O of m cross n as well. So yeah, that's all for this problem. I hope you liked it. Please like, share, and subscribe. Thanks for your time.